when we have linear constraints, it's actually convenient to write them in standard form. So in that case, all inequality constraints will be only non-negativity constraints, and everything else will be equality constraints. So let's see what it means in terms of the specification of the problem. So this is a problem in standard form. So we minimize an objective function, and the constraints are defined by a set of equality constraints. There are m of them. The matrix A has m rows and n columns. And then all the variables must be non-negative. So this is called a problem written in standard form. So let's consider first the equality constraints only. So we have a system of linear equations, Ax equals b, where A is a matrix of m rows and n columns, and B is a vector of Rm. Now, how many vectors x verify this system of equation? Well, it depends. In the context of optimization, if there is zero vector verifying the system of constraint, it's not interesting. There is no feasible solution, so there is no point trying to find an optimal one. There is nothing verifying the constraint. If we have only one, it's not really interesting either, because it's obviously the optimal solution if there is only one solution verifying this constraint, assuming that it also verifies the other constraints. If not, again, the feasible set is empty and the problem is not interesting either. So basically, in the context of optimization, the only case where we have some difficulties or where the problem is actually interesting is when this system Ax equals b has an infinite number of solutions. Now let's look at a concrete system of equation and let's analyze the rank of the associated matrix. So here we have 3 constraints and 4 variables. So the 3 constraints are x1 minus x2 plus x4 equals 2, x3 minus x4 equals 3, and x1 minus x2 plus x3 equals 5. So these are the 3 constraints. So the matrix A is a 3 by 4 matrix that contains the coefficients of these constraints as represented here. So the first constraint has a 1 at the first column, a minus 1 at the second column, a 0 at the third column because x3 is not involved in the constraint, and it has a 1 at column 4 because of x4. And then the 2 is represented in the b vector here. And then we code the other constraints in the same way. Actually, if you calculate the rank of this matrix, you see that the rank is 2, although it has 3 rows. So in the context of linear algebra, we are saying that there is a rank deficiency. The rank is strictly lower than the number of rows. What does it mean? Well, in the context of optimization, it means that one of the constraints is actually redundant. So let's see why. So we write the first constraint here. We eliminate x4. So we write the constraint by saying x4 equals 2 minus x1 plus x2. And now we replace this value of x4 in the next constraint. So we have x3 minus x4, so minus 2, plus x1 minus x2 equals 3. So now let's reorder the variables and move the minus 2 to the other side, and we obtain x1 minus x2 plus x3 equals 5. But this constraint that we have obtained basically by combining the first 2 constraints is exactly this one. So basically the third constraint that we have written is redundant. It does not add anything. In practice, we can actually remove it. It's not necessary. So we can remove this constraint and the feasible set, the polyhedron, will be exactly the same. So let's generalize this result that we saw on the example. If we have a compatible system Ax equals b with a deficient rank, meaning that the rank of the matrix is strictly less than the number of rows, then it means that they exist m minus r constraints that are redundant and can be removed. Actually, it's relatively easy to prove. If you are interested in the proof, I refer you to the book. It's called Theorem 3.6. In terms of optimization, what is important to remember is that we can always assume a full rank, because if the matrix is not full rank, you can identify the constraints that are redundant and remove them, and to obtain a full rank matrix. So it is convenient to write the constraints of a linear optimization problem in standard form. And so meaning that we have a set of equality constraints and non-negativity constraints. For the set of equality constraints, we can assume that it's compatible, because if not, the feasible set is empty, so there is no optimization to perform. And it's actually even underdetermined, so that there are infinitely many solutions that verify the linear equation, so that it makes sense to find the optimal solution. We can also assume it's of full rank, because if it is not the case, there are some constraints that can be removed, and the remaining matrix would be of full rank. About the non-negativity constraints, well, then it means that finding the active constraints at the solution is equivalent to finding the variables that will be zero at the solution. And this is what the algorithm that we will develop later on will do. We will try to identify which variables must be set to zero, that is equivalent to say, because we have a standard form, which constraints are active at the solution.